My name is Natalka. I've been using SQL for almost half my life, and I still have a lot to learn, and I love sharing what I learn. Today, I'm going to share with you how to solve a programming challenge using a single SQL statement. Here's the programming challenge. This is from Geeks for Geeks website. The challenge is, given a linked list of line segments, remove the middle points. In other words, given a linked list of coordinates where the adjacent points either form a vertical line or a horizontal line, delete points from the linked list which are in the middle of a horizontal or vertical line. This was said to be a Microsoft interview question. So for example, take this linked list and change it to this. Now this can be done in a single SQL statement, and I'm going to show you how. No tricks, nothing fancy. We're going to be using simple ANSI standard functions. Now, you might be thinking, I could just do this in C or the programming language of your choice. So for comparison, here's one way to do it in C recursively. This is all one program. This program is from the same website that posted the challenge. And now here's that single SQL statement again, 14 lines long. Bam! One SQL statement and it's done. All right, so let's do this. First, we're going to think about the problem. Then we'll think about the SQL, and then we'll write the SQL. We'll start by thinking about the problem. Let's get back to the challenge. Given a linked list of coordinates, where adjacent points either form a vertical line or a horizontal line, delete points from the linked list which are in the middle of the horizontal or vertical line. Now, I'm going to add an additional criterion to this that wasn't present on the website that posted the challenge. No backtracking. This wasn't explicitly spelled out, but judging from the solution posted on the website, we need to have this or the solution on the website won't be correct. What I mean by no backtracking is I can't go to, for example, 510, 710, and then back to 510. So no backtracking. So let's go back to the linked list we looked at in the beginning. We want to take this linked list and change it to the one below. Let's graph this linked list so you can see a little better what's going on here. There are the points in the linked list. The ones in red are the points that I want to keep. And here's the linked list I want to keep. Or let's take another example, a little bit larger list. Here's that list on a graph. Here are the points that I want to keep. Here are the coordinates of the points. And here's the shortened list. So of course, this has lots of applications. You might recognize a familiar child sketch toy here. Basically, what the question is I want the corners on the sketch. Or in other words, I want the places where the child fiddling with the knobs has changed direction and decided to turn the other knob. Now let's go to an overview of the solution. Since we're using SQL, I want to use set-based thinking. Instead of consuming the nodes one node at a time, let's look at the whole set of nodes and say, which nodes do I want to keep? And how do I identify that a node is a keeper? Going back to my example here, in red I've got the nodes that I want to keep. It's pretty obvious that what I want to keep the first and last nodes of each line segment. So the question is, how do I identify those? Let's look at another sketch. I'm going to throw some points on this sketch, and now, once again, I want to keep the first and last nodes of each line segment. Now, the way that I'm going to conceptualize this, and there are many other ways to look at this, but the way that I want to think about this to make it easier on my head is I'm thinking, I want to keep the node when we kind of change direction. So remember, in this challenge, only one of X or Y can change, not both of them at once. So I'm going to say if the X changed from the previous node, then the direction is X. If the Y changed, then the direction is Y. So for example, take a look at node E here. The X changed from the previous node. So I would say the direction of node E is X. Then take a look at node F. The Y changed from the previous node, so I would say the direction is Y. In other words, right around node E, we change direction. And you can see the same for the other nodes. And then of course we have the end node where there's no direction after it, and the start node where the direction before it is null. So let's put all of these nodes on a chart. I know which nodes I want to keep. These are the nodes I've got in red, and it's pretty easy to say, did the X or the Y change from the previous node? From that, I can get what I'm calling the direction. And then I can see that whenever the node's direction is different from the next node's direction, that lines up exactly with the nodes that I want to keep. So we need to write a SQL statement that lets us identify the node's direction and the next node's direction. That means we need to compare this node's x and y to both the previous node's x and y and the next node's x and y. All right, now we're ready to think about the SQL. The first thing that we need to think about is how are we going to represent the linked list in the database? There are quite a number of different ways to do this. I've got a few up on the screen here. You can move between any of these representations of the linked list with a single SQL statement. So I'm just going to pick this one, which is easy to work with. This is where I've got the x and the y of the node each in a separate column, and the nodes are assigned a sequence number, which is in the order of the nodes in the linked list. So here's the SQL that I can use to create that in the database. Now let's go back to the sketch. Here I've got the first example. I've got the nodes in the database, the x and the y, the sequence number of each. I've got the nodes on the sketch and I've highlighted in red the nodes I want to keep. So once again, I need to write a SQL statement that lets us identify the node's direction and the next node's direction. So I need to compare this node's x and y to the previous and the next node's x and y. Now in general, there's a pattern here. When I have a table and I want to look back at the previous row or forward to the next row, the functions that I'm going to use in SQL to do that are lag and lead. These are ANSI standard SQL functions. Lead lets us peek forward to the next row or to the nth next row over a certain ordering, and lag lets us peek backward to the previous row or the nth previous row over a certain ordering. So for example, I would select the sequence number, lag x over order by the sequence number, lead x over order by the sequence number. And here's the results of running that query. You can see that looking at the second row there, the lead x value of 5 takes the x value of 5 from the third row. And you can see again, looking at the second row, the lag x value of 0 takes the x value of 0 from the previous row, the first row. Looking at the last row there, you can see that the lead x value is null because there is no next row. And looking at the first row, you can see the lag x value is null because there is no previous row. All right, so let's get back to the sketch. We need to write a SQL statement once again that lets us identify the node's direction and the next node's direction. To compare this row's x and y to the previous row's x and y, I'm going to use lag. And to compare the next rows, I'm going to use the lead function. And now we are ready to write the SQL. So I'm going to start with a simple select statement. All I'm doing here is selecting the x, y values, the sequence number, and pretty printing out the node, of course ordering by the sequence number. Now let's add in the lag and the lead for the x and y over order by sequence number. Again, the lag x over order by sequence number gets us the previous node's x, and the lead x over order by sequence number gets us the next node's x, and the same for y. We can see that with a little bit of colored boxes here. Looking at the last x and last y in the second row, they come from the first row's x and y. Looking at the next x and next y in the second row, they come from the third row's x and y. Now I'm going to remind you of that direction concept. If the x changed from the previous node, then the direction is x. If the y changed, then the direction is y. So to get the direction, we compare the last x to x and the last y to y. To get the next node's direction, we compare next x to x and the next y to y. We can do this in SQL using the case expression. Case in SQL looks pretty much like case in any programming language. Here's the syntax. In this case, we're using a searched case expression. It's case, when x minus lag x over order by sequence is not equal to 0, then the direction is x. Or when the y has changed, then the direction is y. Else, n, that gives us the current direction, then comparing to lead x gives us the next direction. Let's pause here for just 1 second and take a look at an assumption that this code makes. I'm assuming that if y has changed, then x hasn't already changed. Or in other words, if x has changed, I don't have to worry about whether or not y has changed. If you recall, that was part of the constraints of this problem, and without that, this code would introduce a bug. Alright, so that's given us the current direction and the next direction. Let's take a look at our sketch again. Again, the nodes highlighted in red are the ones we want to keep, and we can see that those nodes, node 1, 4, 5, and 7, are exactly the same nodes as the one where the current direction is different from the next direction. So we've reached a point where all we have to do is wrap this in an outer statement that says where the current direction is not equal to the next direction. And we have the list of nodes that we wanted to keep. Problem solved. But don't just take my word for it. Let's take a look at this in a live SQL session. Here's the example we just did. Instead of creating a separate table to hold the linked list, I'm using the with clause to include it inline in the query. Here's the linked list we just looked at. Here's the query. Let's run it live. And here's the list of nodes that we wanted. Let's take a look at another one. Here's the second example that we looked at. This is the linked list. The nodes in red are the nodes we want to keep. Let's look at this in a live SQL session. Here's the linked list. Here's our query. Let's run it. And here's the list of nodes: 22, 212, 412, 414, 614, 616, 2416, 2424. Those are the nodes that we wanted to keep. Let's do one more. Here's the sketch we were looking at earlier. I wanted to keep nodes A, E, I, J, K, and N. Let's run this one through the query. Here's the linked list, giving the sequence as ASCII in this case to make it easy to see if we've got the right nodes. And here's the query, and let's run it. Nodes A, E, I, J, K, and N. A, E, I, J, K, and N, just the nodes I wanted to keep. Problem solved. So let's look at what we've done here. We've solved the programming challenge using one SQL statement 14 lines long. We did this with no tricks, just simple use of ANSI standard SQL functions. And what really let us do this is the power of the lead and lag SQL functions. The upshot is this challenge is simpler to solve with SQL. Thank you very much for joining me.